Hello and welcome back. Now, in the last video we did all the data preparation, and now it's time for creating the network structure and training the network. So let's dive into that. So at first, of course, I need to create a new code cell here. So I click on here on the code cell and now define the network structure. So let's call it model. Simply, of course, you can also use it a different name if you want to do that, but let's actually stick to the default one. Let's say model, and this model starts with chars. We also imported chars at the beginning, so we can simply say chars.sequential, sequential, using sequential API. There's also a different API. If you want to use a different one, you can also do that and structure your network, but the sequential one is often used, so we will stick to the sequential one here, right? Okay, and what we need to do now is we put in here a list and simply then start adding layers in here. Of course, you can also say model is chars.sequential, and then you can simply say the other way would be, if you instantiate it like that, just a second, you can also do it like that. For instance, could say the model is sequential and then say model.add, and then you can add layers, right? That will also be possible. But you can also specify the layers directly as a list here, okay? Like that. And let me actually close this here, sequential. All right, here we go. And then you can add different kinds of layer structures in here. So you can simply say, okay, sequential, and then I can simply say for this model, let's say chars.layers. In this case, let's stick with a basic model at the beginning. So the model, if we don't use a convolutional neural network, but we use a normal dense, or let's say a shallow neural network or dense neural network with only dense layers, no convolutional layers, then we need to flatten the data. Because remember, what we have here, we have images. And a normal neural network is not able to deal with images, because images have 2 dimensions, right? Image height and width, and the network would not be able to use this data. If you have a convolutional neural network, we'll see this later on, that would work. But for a normal neural network, or dense neural network, in this case only dense layers, would not be able to process this data. That is why we would have to start with flattening the data. So it's called the flatten layer, flatten, here we go. Of course, 2 parentheses, there are no parameters you need to specify, but that simply means that you have image height and image width, so basically an image, and you squash it, or basically put it that you only have 1 dimension, right? So instead of having 2 dimensions, image height and width, you only have 1 dimension, right? So if you have, for instance, let's say you have an image height of, in our case, we have 300 by 300, image width and image height, and then we simply squash it that we only got 1 dimension here, right? So basically put the 300 images on the same dimension, let's say both on the, on one side, on the width side, for instance, right? If you want to call it that way. So, okay. So we got the flattened data, and now, of course, we could use simple dense layers. So we can simply say chars.layers and then .dense in this case. Let's call it a dense layer here. And this dense layer always needs the amount of neurons in this layer, let's say 512, and then an activation. And the activation which is often used is the reload activation. So it's a really good activation function, at least at this point in time. Maybe in the future there are better ones, but currently the reload is most often used. Or also leaky reload is also available, and other ones. You can also try other ones if you want. We're not fixed to anything, right? So basically creating the model is kind of an art, right? So, okay, so we say chars dot on, let's call a few additional dense layers. Let's call the dense in this case, dense, and then specify, for instance, say 256. So basically half the neurons we have in the previous layer, and then we simply say activation again one more time is reload. So we got this as well, and let's just see. I think there's a layer so dense. There should be a dot, right? There should be a dot dense, and there's only 1 parenthesis. Okay, just make sure that you specify that correctly. And then finally, of course, we got one more layer. So chars.layers. Let's call it the last layer here, and this last layer is also a dense layer. So .dense. Like that, and then specify, okay, well, how many, in this case we have 3 different kinds of neurons. Why is that? Because we got a multi-classification here, right? It's not a binary classification, but because we got 3 different kinds of outputs, rock, paper, or scissor. That is why the last layer needs to have 3 neurons, right? Okay, so 3 neurons here, and the activation is equal to, in this case, softmax. Okay, so at the end, most of the time there are 2 activation functions. It's either the softmax or the sigmoid, and the sigmoid function normally is only used if you have a binary classification, and in other cases you probably most often use the softmax function, as we do here. Okay, so we got chars.layers so dense, 3 final neurons, because we got 3 classes, and the activation function will be a softmax. So softmax simply means that if the values at the end which our network gives us to us, simply in sum is always 1, right? So that's what the softmax does. The probabilities at the end, right? Okay, so we got this, and then we can close this model network structure, and then of course we can compile it. So we can simply say model.compile, compile, and in the compiling option we need to give it an optimizer, which we're going to use, the loss function, and as well as the metrics. So let's say in this case the optimizer is equal to, and it can either refer to keras.optimizers and so on. So keras.optimizers, there we go, dot, and then you can use different kinds of optimizers. As you can see here, for instance, Adam, Adagrad, Adadelta, Adamax, and so on. You can try different one of them, or RMS prop if you want, but you can also do it differently. You can also specify it like that. So if you simply type it in this case in quotes here, and use Adam, that simply means that you use the Adam optimizer. The main advantage, if you refer to keras.optimizers.adam, for instance, you can specify additional parameters. This is not available if you simply use it like I do here and specify it in quotes. Okay, then you would use the Adam optimizer with the default parameters. If you want to customize them, refer to tf.keras. something, right? For instance, here for the loss function, again, if I say loss here, for instance, I could refer to categorical course entropy, or I could also say keras.losses. There's also a losses, in this case, a losses option here, dot sparse categorical course entropy, right? Like here. And I refer to sparse categorical course entropy. Cross entropy, I think this one here should be the right one, with a capital C, and I can call it like that. Okay, that would be the other option to do it. So again, it's up to you if you specify it like that, or you refer to really the class itself in the keras module, if you want to do that, and specify then additional parameters. As you can see here, if I hover over it, you get a function here, and it allows you to specify here the from logits command, for instance. By default it's false. You can put it to true here. You can also customize reduction, name, and so on. So a few different parameters you can specify, or attributes you can specify if you refer to this class like that. Otherwise, of course, you can also refer like here. Okay, so that is that. Okay, so we got this as well, and then of course go on here, just one more thing. Of course, I would like to specify the metrics, and the metrics are always specified in this case a list. So here I'm referring to the accuracy, okay, like that, because we got a classification problem. That is why I'm using accuracy. If you would use a regression, that I would not refer to accuracy, right, as a metric. Okay, so we got this as well, and then finally, of course, we can well call the model.summary. Just to give an idea of what the model structure looks like. If we run this, let's take a look. Model compile, model.summary, and I got an issue here. This model has not yet been built. Build the model first by calling .build method. Okay, so I need to first fit it. Let's actually take a look at that. So go in here and say model.fit. Let me actually train it first. Fit, and then call train, and actually specify that in history. History is equals to model.fit, train, like that. And then of course what we need is the train images we specified, and also the train labels like that. And then we also say epochs is equal to 5, and the batch size is equal to 32. Okay, let's do it like that, and let's actually run this and store it in history, and you can see that it's running. Okay, so that's obviously fine, and you can see it's pretty fast, right? Why is it pretty fast? Because the network itself is an easy network, right? We only have those 3 layers, and the last one is of course then the output layer, and we do not specify, for instance, we don't have any convolutional layers and so on. So it's pretty easy network concerning the structure, and that's why we can run it, and it's run pretty quickly, and we already get a loss here, starting with accuracy of 45%, but at the end we had 82% accuracy, okay? Which is not bad. Not totally bad at least, but it's also not really good, right? So we would like to have something more than 82.3%. Okay, so what could we do? Well, the next thing we could do is actually we could create a more advanced model, for instance, a convolutional neural network. But before we do that, let's actually evaluate also what the test output is. Okay, let's go in here and say model.evaluate, evaluate like that. And then of course we use the test images, so test images, as well as the test labels like that, of course. Okay, so evaluating simply means that, okay, on the training data set we get 82.3% accuracy. That's not too bad, also not too good, but at least 82%. But what about the test data, right? Because the training data, the model was trained on the training data. But what if it sees now data which has not seen before, right? Or the test data. We can also run this and take a look at what the evaluate output gives us. And you can see that here the loss is 2.59, and the accuracy actually is below 50%, right? So pretty bad, actually, right? So here, don't get confused or don't misinterpret this and say, okay, accuracy is 82%, well, that's pretty good. But if you take a look at the test data, so unseen data, you can see that the accuracy is only 41.67%, which is not really good, right? So even it's below 50%, so it's really not good. So obviously, this model structure, as we currently have, is not enough. So we need to define a more advanced model and need to get better accuracy. And this is something we cover in the next video. Until then, best guys.